Hello, vintage computer friends. So today we have the wonderful Microprofessor MPF-1 Plus again on the bench, and I'm going to show you how to use PicoRAM 6116 as well as the Z80 online assembler to implement the towers of Hanoi for this machine. And if you recall, then in one of my last videos I showed you how to do this on the Microprofessor MPF-1. The 1B, right? And that is of course a predecessor to this machine, and we used the same development toolchain, right? So Z80 as well as PicoRAM, right? And PicoRAM is of course an SRAM emulator, so it plugs into the U5 6116 SRAM socket here, right? Replaces this chip with a SRAM emulation that's run by the Raspberry Pi Pico. But it's also equipped with an SD card interface here, right? So you can just put your hex files, your program, onto SD card and then load it directly into the memory, right? So that doesn't even require like something like a serial interface or whatever. It simply emulates the SRAM, and all programs that you basically load over SD card into the Pico will just manifest immediately into the memory region of the microprocessor, right? Which is of course quite a bit more comfortable than having to fiddle with, a serial interface and terminal programs on the PC, etc. So yeah, and I've already prepared this program for you, right? It's already here on the SD card. You can see that it's loaded Hanoi, and we can start the program, right, at address F800. G is for go to, right? And unlike the MPF-1, the big advantage of the 1 Plus is of course that it has this wonderful VFD, right, voltage vacuum fluorescence display, right, which is giving you alphanumeric output, right, rather than just, the 7-segment display that the Microprofessor MPF-1 or 1B have to offer, which makes this of course a much more versatile and powerful machine, and it even has a full alphanumeric keyboard, right? So this program, Hanoi program, is quite a bit more comfortable than the one that we wrote for the MPF-1 based on these capabilities, right? So here it's now asking us for the number of disks we wanted to solve the Hanoi problem for. Whereas in the MPF-1 version, we simply had this as a constant in the code, and we needed to change that memory location with a monitor, right? But here we can now enter 1 to 9 for the number of disks, and let's play with 3. And also we are utilizing the display now to show the moves, right? And the display duration that it shows each move for in terms of millisecond, we can also now determine, right? Because if you play with 8 or 9 disks, then it takes a while if you have like a large long display delay, right? So, and here we are playing with 3 disks now, and I can now just push a button, right? And the ASCII code is then basically used as a delay, right, of that button. Yeah. So here for space, this gives a reasonable delay. Okay, and ready for another round, right? And if we now play with 9 disks, we want to use a fairly low delay value, right? So I can, for example, use Ctrl G, which is 7, and then it runs quite fast, right? So, and like last time, we are going to use the online assembler Z80 in order to program the assembler code for this, right? And I'll show you the differences to the MPF-1 version. In particular, the firmware is much more powerful, and it has many more firmware routines to offer than the MPF-1 version, right? Which allows you to do all these wonderful things with the display, like putting a text string on the screen, right? Things that you of course can't do with the MPF-1 because it doesn't have an alphanumeric display but only a 7-segment LED display. Okay, so like for the Microprofessor MPF-1 or 1B as we used in our previous video, we are using the online SM80.com assembler again to compile the hex file, right? And The program for Hanoi for the Microprofessor 1 Plus is of course very similar. In particular, we are going to use the stack of the Z80 again, and we are going to use the same macros that we had in the previous version, right? Push all and pop all, and we are just putting all the major registers, saving them on the stack, and retrieving them from there as needed, not only for the recursive calls during the execution of the recursive version of the Hanoi program, but also to protect the registers from the firmware, the system calls that we are going to make in order to put content onto the display, to make a sound, or to read input from the keyboard, right? And so first of all, PicoRAM 6116 replaces the U5 RAM chip on the Microprofessor 1 Plus, and this is starting at F800 here on my machine, but that might be different address for your machine, because there is an internal modding possibility for the address range for the U5 chip basically, right? So double check if that is the same on your machine. F800 here. And so let's start with the main part of the program, right? And again, we are using the registers A, B, C, and D. So A contains the number of disks, right? B contains the source, C the target, and D the spare or intermediate pack name, ABC here. And then we are calling Hanoi. Also, we are making these beeps, right? And they're actually the firmware routines that make these 1 kilohertz and 2 kilohertz tones, right, over the loudspeaker. They are also called tone 1 and tone 2. So that's a nice thing. They actually try to keep, at least for the naming and the calling conventions of these firmware routines in ROM, they try to keep the naming consistent between the MPF-1B or MPF-1 and the MPF-1 Plus firmware, right? So, and then, so the main Hanoi program is very similar, right, to the MPF-1 version. So first we check again if the base case has been encountered, right? That means is there a 0 in the accumulator? In that case, we are basically done and return. And else, I mean, we are now saving the registers to the stack. We are decrementing the disk number, we are shuffling the pack names around, right? And then we make the recursive call here. And again, I should not be should not be double clicking on a line in order to highlight a line. That doesn't work in SM80. And then when we return from the call, we restore the stack to the previous values. Now here's the difference, right? In the MPF-1 version, I had basically had to prepare an output buffer for the firmware so that we could actually put values onto the display. We had to save the A, B, C, D registers into certain memory regions, which was the basically input text buffer, right, which would then be converted by a firmware system call into 7-segment LED bit patterns, right, on and off for the individual 7 segments of the display, and that would then be put onto the display. But here, I mean, the firmware is a little bit more comfortable in the way that we don't need to manage and set up this output buffer basically for the text or the values that we want to display ourselves, but the operating system, the firmware, is already maintaining these 2 pointers automatically for us, so we don't need to pass along basically an address and set aside a designated memory region for that. So we are just calling the movement routine, which basically now puts the text on the display, what is happening to which disk, from what pack to which pack is it being moved. We want to now put the message move onto the display, really in alphanumeric text, right? And for this, basically, we have the message basically as a string in memory here, move, right, and a space, and the strings have to be terminated with what's this? 0D is carriage return, right? Z13, so have to be terminated that way. So that's the printing routine, print message, right, a firmware routine. We then simply look at the HL at the pointer that points to that string and puts it on the display, right? It also clears the display first, and the display also has an automatic cursor, so you can basically print, make subsequent calls to printing routines, and the cursor will be automatically advanced for you, right? Which is very comfortable, of course. And this print message routine is at address 0886, right? Doesn't really matter, but of course it's also well documented. So the listing here is alphabetic, right? So I'm pretty sure we'll find that here if we scroll down. And yeah, there it is, right? So it does multiple things. It calls message, which is responsible for the output, displays the contents of a memory range on display, and prints the same with the printer also. So if the printer is connected, then it will also put the message on the printer. I don't have the printer connected here, but yeah, that's comfortable. And HL is just the pointer to the starting address of the memory range. So that's what we're going to use to put this move message on the screen. Then we want to next we want to now print a hex number, a single digit hex number, namely the disk number, move disk 1, 2, 3, 4, right? And first of all, we are always using push and pop around these firmware routine calls, because they might destroy our registers, right? Because we now have the registers A, B, C and D, A, B, D and E loaded, right? And we need to have them preserved between the different firmware calls. And in order to now convert the disk number, which is in the accumulator, we can simply call hex 1. And hex 1 is another firmware routine at 0AAD. And what it does is it simply puts the hex number that is in the accumulator onto the display, right? And it also manages the cursor and advances the buffers automatically for you. Converts the least significant 4 bits, so it's nibble only, right? In register A, binary data to ASCII code and display pattern. And yeah, that's what it does. So this is how we now have move disk number, move 1, move 2, move 3 on the display. And now we got a we want to put the message from this pack to that pack basically onto the display, right? So again, we have a string here in memory, namely string from, again terminated by carriage return, and also a to message string in RAM in memory. So we are printing the from message. And now we have to print the source pack hexadecimal number onto the screen, A, B, or C. We are loading the source pack name, which is in B, into the accumulator, and calling hex 1 again, right? So we now have the source pack on the display printed. Then we are printing the to message here, right? So, and then we are also printing the destination pack number in hex on the screen. So that is basically the screen output, right? Move 1 from A to B. So that's the pattern. And all of these calls are being protected by push all, pop all, our macros, right? Because as I said, these firmware calls might be destructive and alter the registers. So we need them preserved. And we also want to have now, because the machine is obviously otherwise running very fast, we want to put a delay loop in here that is basically this time configurable, right? So I have basically a speed, display speed number here in this memory cell speed. So yeah, this is the major difference, right, to the MPF-1 version of that program. We just need a different output routine that puts the move on the display, right? Because we now have a very comfortable full alphanumeric display and not only a 7-segment display. Yeah, so basically that's the same program. And yeah, That's the only difference here basically, and of course the movement subroutine as just explained. But we also wanted to take some advantage of the display and make the program more comfortable to run, and that means we also want to give the user this time the ability to input the number of disks over the keyboard when the program starts, right? So in the MPF-1 version I simply had basically the number of disks loaded literally in the code, right? So load 3 into the accumulator or so, right? Whereas here I'm now printing message disks, and that basically says, okay, number disks, question mark, right? And then the microprocessor is waiting for keypad input, for keyboard input, using this routine here, this firmware routine, scan2. And what that does is it scans the the keyboard, right, until a button has been pressed. So similar to that of scan1, but differ with scan in two respects. Scan1 only scans once, while scan2 keeps scanning until a key is pressed. Scan1 gets a position code in the accumulator as a result then, and scan2 actually gives you an ASCII code, right? So knowing ASCII, of course, we now need to translate this into the ASCII code into number, right? So ASCII code for 0 is 48, for 1 is 49, so we simply subtract 48 then, and now have the number of disks 0, 1, 2, 3, etc. up to 9. So it's only a single digit input that scan2 supports, right? But up to 9 disks, that's already keeping the machine quite busy, right? 2 to the power of 9 is like 512 minus 1 is 511 moves, right? And also now we want to determine the speed, the display delay, right? How long does the display actually show us that move message, right? So because if you now like support up to 9 disks, right, and that's 511 moves, then you really want the display to run quite a bit faster, right? Whereas for 3 or 4 disks, I mean, maybe you want to play along with the output using your wooden disks and packs, right, or your stack of coins, right, and then you need a little bit more time. So I decided, rather than, you know, allowing now 2 or 3 digit input of decimal number to specify the delay in milliseconds, let's just use the ASCII character basically, right, and use that as a delay. So again, I'm outputting now a disk, a message here, right, message speed on the display, which is the prompt for the input, disk speed here, right, and then I am again calling call2, so scan2, and that now gives me the ASCII code of the letter that we pressed on the alphanumeric keyboard. Yeah, so and then I mean we just prepare. Now we have the disk numbers, and we put this into memory, right? So there's a designated memory location speed, so that's where we store the delay speed byte, and then we initialize B, C, and D with source, target, and intermediate pack names A, B, C, and we just call Hanoi. And yeah, when the program returns, we make another confirmation tone, right? And so the previous version just executed a halt here, but of course it's nicer if the program just restarts itself, right? And then you can, you know, play another round of Hanoi with your microprocessor. Yeah, so that's the MPF-1 Plus version. Now let's assemble this, right? Compile this. Okay, no problems. And again, we are now looking at the generated hex, and I already have Emacs sitting in the background here, and I can, you know, copy and paste this. Copy. There it is. And again, I mentioned that last time, so the first 9 characters that are produced here, right, that's the address, 8 nibbles and leading colon, so we just remove that. For this we can use the rectangle mark mode, very comfortable in Emacs, right? And then you can just, you know, snip that out like this, and it's gone. And the last byte is a checksum, has to go. Quick and easy. And this also, the last line has to go. And this is then, you know, being saved to your SD card. And you put it in PicoRAM 6116, and we see what we get.